Hi everyone. Today I want to talk to you a little bit about the relationship that exists between math and science. Um, by way of introduction, if you're not one of my students, my name is Gary Strickland, Mr. Strickland, and I teach high school physics and IPC. And one of the things that I've noticed over time, taught at the middle school for a long time as well, and one of the things that I really noticed that concerns me is I have a lot of students that tell me they love science. It's one of their favorite classes. They like to come in, they always enjoy experiments, they want to do things, but whenever we start talking about the mathematics that are involved, this is the face that I end up seeing on a lot of my students, and that troubles me because the math really informs us about the science. And I don't think we always make it really clear to our students what this relationship is, and I don't think we work hard enough to find a way to make it less scary. So that's what we're going to do today. This ladder of abstraction is an idea that I got from a gentleman named Dan Meyer. You can look him up on the internet, fascinating and great mathematics instructor. And he's the one that gave me this idea, because if you think about what a ladder is, it's a device that we use to go one rung at a time to get from one place to the other. We can either get from the ground to the roof of our house or vice versa, get from the roof and get back down. And an abstraction is a scary sounding word, but it shouldn't be. An abstraction is just something that exists as an idea. So we're going to talk about how we get from concrete things in the real world to ideas. We're going to start. I wanted to mention this quote by Albert Einstein too. He says that the formulation of a problem is often more essential than its solution. And I think what he's saying here is that being able to traverse this ladder of abstraction, seeing some real world event that's fascinating to us or that we're interested in, and how to get from that real world event, and by either gathering of data or elimination of things that we don't need, how do we get to some mathematical solution or mathematical problem. Now once you get the problem defined, then he says, well, it's merely a matter of mathematical or experimental skill. Now those skills may be significant, but we're down to computation at that point. So let's jump right in and see how this works. See what this relationship is. So let's look. Okay, we start with some real world situation, something that fascinates us, interests us, or maybe some problem that we have, but there's some event that's in the real world that we want to look at. And so what do we do with that? Well, okay, if I can get my thing to work here. All right, we take this real world situation and we try to find some way to formulate that real world situation mathematically in some way, to give it some kind. We use mathematics because mathematics is all about logic, and it's about quantifying things and being repeatable. So we take the real world event, try to find some way to define it mathematically, and we use our knowledge of mathematics and algebra and the calculus to arrive, hopefully, at some sort of mathematical solution that we interpret in some way to reveal some kind of real world solution that informs us in some way about or addresses this real world situation that we had to start with. And to me this is pretty fascinating, because if you look closely at what we have here, over on the left of the screen, these are the things that are concrete. All right? And over on the right of the screen, we're looking at the things that are abstract. So our mathematical problems and solutions are abstractions, but they're rooted in the concrete real world. They're in science, okay? And I think that's a fascinating connection. We have to be able to move back and forth from the concrete to the abstract and from the abstract to the concrete. We have to be able to do that nimbly in our minds to really appreciate what science does. In fact, it's really pretty fascinating in the news recently. Here's a picture of Peter Higgs and some of his calculations. All the way back in 1964, Peter Higgs had a mathematical construct and a mathematical solution that predicted a real world particle, the Higgs boson. And that's been a quest of physicists for a long time, is to try to find a concrete proof of this theoretical or abstract idea. And this year in 2012, at the Large Hadron Collider in CERN, they've tentatively confirmed the existence of this particle that was predicted all the way back in 1964 by Mr. Higgs. And so that's pretty fascinating and a timely example of what we're talking about. Now, in the midst of all of this flowchart, we have our knowledge of the symbols that we use in mathematics, mathematical reasoning, and the computation skills that are required to facilitate this flowchart. And unfortunately, that's where people spend their time, that's where they focus, and I think that's all there is to it. But as you can see, that's only a small part of this relationship. All right, so now let's move and see how this might work in the real world. All right, so here's a nice picture, and we're going to start with a concrete thing, and we're going to move towards an abstraction. Well, this is a picture that could be of any number of streets in any number of small communities anywhere in the United States or elsewhere in the world, perhaps. And we go, well, it's kind of boring, and I took it intentionally for it to look boring, because we have to start asking ourselves, well, why did you take the picture? What's important? And that's one of the questions that we ask in science. Well, what is important here? Well, maybe this is the first week of school and mom's just backed out of the driveway, and we're trying to figure out the best path, the best way to get our kiddos to school. Well, can we think of a better way to analyze it than just looking down the street and wondering whether to turn right or left or go the other way? Well, maybe so. Well, here we've stepped up a rung on this ladder of abstraction. Well, now we're looking at an aerial photograph of the community where we are. And just so that we kind of can get oriented here, here is our school. And we're going to try to find the best way to get to here. All right, so aerial photograph still has a lot of information that's not relevant to our discussion here about how to get to school. So let's abstract this a little further. Well, we can overlay this with lines of longitude and latitude, so at least we can locate where on the planet this is, but I don't know, did that reduce the amount of information or did that increase it? In some ways it increased it, and it's not getting me to what I want to know. So can we abstract this in a different way? Now this looks better because we've reduced the amount of irrelevant information and getting down to maybe what's important to us. So now the question is, how do we get to school? And well, what can we do to analyze that? All right, well, let's take a look at this. Okay, let's say maybe that we live here. Well, we leave the house, go down the street, and when we get to the corner, we turn till we get over here to this main street, turn south, turn into school, into the parking lot, and then turn into our parking place. That's the path that we're going to take to get from point A, over here where we live, to point B at the school. All right, that's some relevant information. What if we make this a little bit more abstract? All right, now we just have the arrows that we just drew. And this is sort of interesting because, okay, well, how's that interesting? What does that do for us? Well, we'll start to talk about vectors later in school. Now, what if we take these arrows and now we've got some north-south direction that we moved? Well, we went east, but then also we turned back west, and maybe we can evaluate that in some way. What is it that we really wanted to know there? Okay, well, I don't know. Let's see. Let's put another arrow on here that might be something interesting to us. Maybe what we really wanted to know was what this displacement was, how far it was from home to school, and how long it took to get there. Now we're really starting to turn into something that really is pretty abstract. You know, getting a little bit ahead. We'll talk about these more later, but we've got some vectors here. Well, okay. Well, what if we called this net distance here A, and this B, and this C? Well, then all of a sudden, maybe I've got some kids going, hey, I know this. C squared equals A squared plus B squared. So the distance C might equal the square root of A squared plus B squared. And all of a sudden, we're at this mathematical abstraction. We have, you know, some formulas here. We have a function that informs us in some way about the question that we had. Isn't that really cool? What else could we look at here? Well, all right. Let's look at this some other way too. Can we graph some of this information? If we make a graph here. Well, what were the things that really interested us here as we look at this? Well, we wanted to know how long it took to get to school, and we wanted to know how far we have to go, and so how fast do we have to drive to get there? Well, that's kind of interesting, because if we follow the red path here, we get one set of answers. All right, let's kind of look at that. If you follow that red path, originally we had to go a large distance over some amount of time, so maybe we had to drive pretty fast. But maybe the question then becomes, well, what was the velocity if we look at the displacement over time? Well, we're going to talk about that more later. But the displacement was much less distance, but in the same amount of time. And so now we've got some way to graphically analyze this real world situation that, if you remember, we started all the way back there with the street. All right. So now let's look at these things. We narrowed it down to the information that was truly important to us, the distance and the times that were involved. And interestingly enough, going over here, there are only 7 fundamental dimensions or units that we use in the International System of Units that allows us to describe most things in the world. One of those is length. Length is always there in things that we're measuring. Mass and kilogram, time, electric current, not relevant in this problem, but will be in others. Temperature is often important. How much of something is involved is often very relevant. And luminosity, the luminosity of an object, how much light's present. These are the 7 fundamental dimensions that actually, amazingly enough, allows us to describe, at least using classical mechanics, most things in the world. And by way of demonstrating that, let's look at this chart. Over on the left, we've got the 7 fundamental units that we find in the International System of Units that we just mentioned there. And then we've got 22 common derived units that come from comparing these base units. What we just talked about, if we compare length and time in terms of displacement, maybe we get velocity. Well, how does the velocity change over time? Well, that gives us acceleration. Well, what if we compare the acceleration of an object with its mass? That leads us to the Newton, a unit of force. And so you see how, as we start to get towards these derived units, some of them, over here, power, heat flow, resistance, capacitance, electric charge, all of these things, energy, work, and quantity of heat, and you can go back and using some analysis, you can figure out what the base units are that allow us to discuss those situations. All right, I think that's pretty fascinating. So when we do dimensional analysis, that's really what we're doing. We're going to look and see what those base units are, those base dimensions that make up the situation that we're exploring. All right, so this relationship, like in our example, between distance and time. A function is just that relationship that defines the situation in terms of a set of interacting conditions. And those interacting conditions are those fundamental units and derived units that we're interested in. We have formulas that are mathematical representations of the function. And then functions, sometimes we analyze those graphically because that informs us very well about what we're interested in. So now over here we're embedded in the math, but I hope you see how this math is a result of the questions that we had that fascinated us about the real world. So in summary, here's what I hope you get out of this. In science, we make observations of the real world, and we decide what things fascinate us, what questions need answering. Are we interested in finding a cure for cancer? Are we interested in how long it takes to get to school? Some of our questions are quite profound and some are quite simple, but that's where we start. And then we develop some structure or way to quantize and evaluate that situation. That's where our mathematical reasoning skills come in that I think Mr. Einstein was referring to. Once we've developed that structure, then we identify the steps that we need to follow to solve our problem and answer our question, and then ultimately, finally, we use our mathematical computational skills to solve the problem, and then hopefully take that answer and see how that informs us about the world around us. So I hope what we've done here briefly is show the relationship that exists between math and science, and show that it's not so scary, that we start with real world situations, we make them abstract, or like in the case of Mr. Higgs, sometimes we have some abstraction and we look for proof of that in the real world. The two are inseparable, and I hope this makes that a little bit less scary for you, and thanks for listening.